Hello students, Halverson here. We are studying the beginnings of physics, classical mechanics. For those of you who are just joining us, we are using this textbook here. It's Physics by James S. Walker. It's the 4th edition. Now, it's been superseded by the 5th edition, but I'm sticking with the 4th edition because it's easy to get through eBay and Amazon, and there are many used books out there. And so this book is very inexpensive, and it's just as good as the much more expensive 5th edition. Okay, now we're just using volume 1, and that's the one for classical mechanics. Now in this video, we're going to be getting into chapter 2, kinematics. And so let's get started with that. So kinematics means the description of objects that are moving. And to keep things simple for now, we're talking about moving in just one dimension. All right, so let's start with a bunch of vocabulary. The position of an object is where it is, and it gets the variable x, usually. I mean, it could be another letter, but for now we'll use the letter x. Later on, if we get into two-dimensional kinematics, we'll use x and y. And when we get to three-dimensional kinematics, x, y, and z. Okay. Now, if you move from one location to another location, that we would say, okay, we have an initial x called x sub I, and then we've moved to a final location, a final position, which we'll call x sub f. And then the displacement, so this is a new word, we're going to call that delta x, and a delta means a change, so the change in position, which is equal to the final minus initial positions. Now, this is an important thing to keep in mind. A change is calculated by taking the final amount and subtracting the initial amount. Keep that in mind. It's easy to forget and then get things backwards. Okay. Now, there's also distance, but distance is the absolute value of the displacement. You see, the displacement could be negative, right, since this is a subtraction, but the distance, we ignore whether it's to the right or to the left. We ignore the direction and just use the absolute value of the amount. All right, so the distances are always going to be positive numbers, whereas displacements can be positive, which would generally mean to the right, or negative, which would then be to the left. So let's have an example. We have a skateboarding physicist here, and she starts out at location x sub I, equal to 3 meters, and a little while later she's at x sub f, the final x, which happens to be 8 meters. So to calculate the displacement, the delta x, we do the final x minus the initial x. Well, the final x is 8 meters, and the initial was 3, so it's 8 minus 3. So the displacement, delta x, is 5 meters. And I put a plus there to indicate that it is in the positive direction. And I also put this arrow here pointing to the right to kind of reinforce that it's to the right. And later on, we're going to be calling this sort of thing a vector arrow. And the whole thing is a vector. So remember that vectors are numbers that have a direction that goes with them, whereas scalars are just the numbers, but no direction. And that, so here's an example. The distance is the absolute value of the displacement. So our skateboarder moved 5 meters, but we say, okay, it's a distance of 5 meters. But when you say that, you've lost the information as to whether it was to the right or to the left or maybe up or down. So a distance is just, that's it. It's a distance, but without any knowledge of the direction. Okay. Now, here is a little twist on the example. What would the displacement and distance be in this case? You see, in this case, we have the initial position being 8 meters, and then the final position being 3 meters. So I'm going to let you think for a few seconds here, and so think about it. What would the displacement be? What would be the distance? All right. Now, I'm going to make available the answers to all of these notes. For my Mt SAC students, the answers will be on Canvas, but I'm also going to be putting them on my personal website, which is halverscience.net. Okay, so let's do this. So the displacement, I'm going to write this all out, is delta x, which is the final position minus the initial position. And let's see, now the final position is 3 meters, and the initial position is 8 meters. 3 minus 8 is going to be negative 5. And so the displacement is negative 5 meters. And then I could add to that a vector arrow, which in this case is pointing to the left, which is the negative direction. And that would be the vector for the displacement. Right. Now the distance is the absolute value of my negative 5 meters. And so clearly that's going to be 5 meters. Okay. Now let's talk about speed and then about velocity. So in chapter 1, we said that speed is distance over time. And as far as time is concerned, let's get a little bit technical. It's really the amount of time that elapsed during the experiment or the measurements or whatever. And we call that delta t. And then delta x is the distance. And so the speed is the distance, delta x, over delta t. Now, this is actually telling us the average speed, which means that we don't know much about what the speed was between the beginning time, the initial time, and the final time. It is possible that the speed was changing. It could have been the skateboarder could have been going fast and then halfway through the experiment slowed down, and we wouldn't know that from this sort of math because we only know the beginning and end information, position, and times. Okay, we'll take care of that problem later on. But for now, this is just the average speed. Now, the distance, like I mentioned just before, doesn't have the direction information in it. And so this speed v here doesn't have any direction information either. We don't know if the skateboarder is moving with a certain speed to the right or with a certain speed to the left. We just don't know that from what we have here. And so the distance is a scalar, and consequently the speed is also a scalar, which is not really what we want. We really like to have the directions, and so we upgrade. Instead of speed, we're going to talk about velocity. Okay, so now our delta x it's been upgraded. I mean, I realize that it's the same notation. It's also delta x, but now this is the improved delta x, which we're calling the displacement, and so it takes into account direction. And so the average velocity is delta x, the displacement, over delta t, the elapsed time. And we can write it this way. It's the final position minus the initial position, all of that divided by the final time minus the initial time. And since this new delta x does include a direction, the velocity now does include the direction of motion. So here is an example for velocity. So going back to the previous example, the one where the skateboarder was going to the left, the negative direction. What is the velocity? And then I'm also going to ask, what is the speed of the skateboarder? And I'm giving you some new information here. We've got the initial time of 0.6 seconds and the final time of 0.85 seconds. So take a look at this. What should be in these blanks? All right, so you thought about it? All right, well, if you go back, you should remember that the final position was 3 meters and the initial position was 8 meters, and 3 minus 8 was -5, which is what we did before. Put in the symbols here, T final and T initial. Okay, and then here are the times. The final time, the initial time. And 0.85 minus 0.6, you have to do a little math, turns out to be 0.25 seconds. A quarter of a second. Okay, so now the average velocity. Delta x over delta t. So we've got delta x is -5 meters, right? Coming from there. And delta t is 0.25 seconds. Yeah, so that's this right there. And okay, so dividing by 0.25, well, 0.25 is a quarter. When you divide by a quarter, it's like multiplying by 4. 4 times 5 is 20. And don't forget the negative sign. So our average velocity for the skateboarder is -20 meters per second. And you knew that. Yeah. Okay, and then the speed, well, it's the absolute value of -20 meters per second, which is, of course, positive 20 meters per second. All right. And so that's the speed. All right. Okay, now I need my students to be reading the book. And in particular, they need to work all of the examples in the textbook. And I'm going to be giving a quiz on the examples. So to be ready for my quiz, you've got to look at the examples. You've got to do the examples. Yeah. All right, next topic. When we do kinematics, we will be doing a lot of graphs. We're going to have position graphs, velocity graphs, and also acceleration graphs. So now look at these axes here. Notice that the horizontal axis is not the x-axis, no. And the vertical, right, the up and down axis is not the y-axis, no. No, actually, The horizontal axis is time in seconds, and the vertical axis is x, position in meters. Okay, so let's fill in these blanks. So horizontal axis means time, right? And the units, of course, are seconds. And the vertical axis is position. And the units is going to be meters. Okay. So let's have an example. This graph here could be describing the example before. So this, I'm referring to the example where the skateboarder started out at 8 meters and ended up at 3 meters. All right, so let's look at this. The initial time is 0.6 seconds, right? That's the initial time. And the initial position is 8 meters. There, okay. I wrote it here. So ti is 0.6 seconds, x sub I is 8 meters. And similarly, the initial time is 8.5 seconds, and I said initial, I should have said final. The final time is 0.85 seconds, and the final position is 3 meters. Okay. I drew a straight line here. Now, this may or may not be accurate, the line itself. The problem is that it's possible that the skateboarder was speeding up or slowing down, in which case this line would be curved. The fact that I drew a straight line means that to be totally accurate, the skateboarder would have to be going at a constant speed, not slowing down or speeding up. But that's just a limitation of our approach here. We'll do better later on. But for now, this line here is trying to describe the motion of the skateboarder. Now, this line is sloping downward. And so that's a negative slope, right? So a positive slope would be sloping upward, negative is sloping downward. And so that tells us right away that the velocity, our skateboarder's velocity, was in the negative direction. And in fact, we can go further than that. We can say that the slope and the velocity really are the same thing. At least they're the same thing when we're talking about a x versus t, a position versus time graph. Okay, you may notice I just changed shirts. I'm now wearing my University of Arizona shirt here. It's just way too hot to be wearing that nice white shirt. Okay, so now let's take a look at a fancier example, something that'll exercise your ability to work out kinematics problems. So we once again have a position graph. The horizontal axis is time. The vertical axis is position in meters. Time was in seconds. And it could represent the motion of some weird object because it's moving in a slightly strange way. Maybe it's a robot. And it's going back and forth. So now I've divided the problem up into different time segments. So time segment A, B, C, D, and so on. So let's take a look at what the motion of this robot is like. All right. So it starts at 20 meters. And so here, I'll just put a dot there, 20 meters. Now half a second later, it's still at 20 meters. And a second later, it's still at 20 meters. That means the velocity is 0. But you know, I knew that already because this line is horizontal. The slope is 0, which tells you right away the velocity is 0. Now, in time segment B, starting at 1 second, the slope is negative. It's downward. it's negative. So that means that the robot is moving in the negative direction to the left. And then in time segment C, it's turned around. This is a positive slope. The robot is now going to the right. And not only that, but the slope is steeper than in B, so the speed is more. Okay, and then in D, it's going in the negative direction, negative slope, and it's equally steep. I think that should be clear. The symmetry of this triangle makes it clear. So the speed in C and D are equal, although the velocity is positive here and negative here. So going to the right, going to the left. The slope is less in segment E, so it's slowed down, and then it's sped up somewhat in F. And then what's happening in G? What's the robot doing? So if you noticed that the slope is 0, and then you said, that means the robot has stopped, at least for this period of time, you were right. Good. And then the robot is moving to the right, the positive direction here in time segment H. Okay. So what I would like for you to do is to fill in these answers here. And I'm going to post the solutions, the answers to all of these notes on Canvas, for my students. And if you're not a Mt SAC student, you can still access my notes and my solutions and so on by going to my personal website, which is halverscience.net. Okay, so let's get you started. I'm not going to do it all, but I'll get you started. So let's, first of all, let's write down what these are equal to, right? Just to remind ourselves. So delta x is equal to the final position minus the initial position. This is the, delta t is the elapsed time, and this is the final time minus the initial time. And this is the delta x over delta t, the displacement over the elapsed time. And then this is just the absolute value of the velocity there, okay, which is what I said anyway. Okay, so let's do this. For the displacement in segment A, all right, well, the final position is 20. The initial position was also 20. And so this is going to be 0, and the units are meters. How about for time? The final time was 1 second, and the initial time was 0 seconds, and so we end up with an elapsed time of 1 second. The velocity is delta x, which is 0 meters over 1 second, so that's 0 meters per second. And the speed is going to be the absolute value of 0, which is 0 meters per second. Yeah, so that was boring. But B is going to be much more exciting. Let's do B. So the final position is here, right? This is the final position. Okay, so it's 0 meters. The initial position is 20 meters. And so this works out to negative 20 meters. The elapsed time is 3 seconds minus 1. So here we have 3 minus 1 gives us 2 seconds. And okay, so the velocity is going to be negative 20 over 2, which will give us, is that right? Yeah, negative 20 over 2 will give us negative 10 meters per second. Yeah. And then the speed will be the absolute value of -10, which will be 10 meters per second. Okay. You got that. We'll do one more. I'll do C and then see what happens next. I'll let you guys work out the rest. So for C, we have delta x. Okay, so the final position is 30. Here, let's do this with a different color just to clarify things. Okay, so here we're doing C. So the final position is 30. The initial position is 0. So we get 30 meters. For the elapsed time, the final time is 4 and the beginning time is 3. So we have an elapsed time of 1 second. So then the velocity is 30 over 1, right? 31, which gives us 30 meters per second. And the absolute value of 30 is also 30. So the speed is 30 meters per second. Okay.